Okay, I think that's recording. Okay. So, nobody at the office hours again. This is a recording just to leave some notes on homework in case people find it useful. This homework is split between the end of the chapter on quantum mechanics and the start of the chapter on statistical mechanics. So let's just run through the questions in this week's homework. Question 1, if a perturbing potential does not change the wave function of the unperturbed system, what is the correction to the nth eigenstate? So this is an obvious problem. There is obviously no correction to the nth eigenstate if the perturbing potential does not change it. But I want you in this question to write down the expression for first order perturbation theory. So this tells you that for the nth eigenstate in perturbation theory, it's equal to the nth eigenstate of the unperturbed system plus this term, I'm not going to bother writing down here, just the sigma sign, which is the sum over the perturbing Hamiltonian and the unperturbed wave functions. I want you to show why that sum is 0 using the properties of the unperturbed eigenfunctions. It's very simple and straightforward, just using the properties of the wave functions when they commute with the Hamiltonian. All right. B, if a perturbation of energy is to drive a system from energy En to energy Em, so this is time-dependent perturbation theory, what two conditions apply according to Fermi's golden rule? So I want you to tell me, looking at the equation for Fermi's golden rule, there are really two chunks of it, one having to do with wave functions, another having to do with energies, and I want you to tell me in words what conditions need to be satisfied for the transition rate to be non-zero. Question 2. This is also about perturbation theory, and so we're taking a look here at the ground state of a harmonic oscillator. So the potential energy has the form E is a half kx squared, or the Hamiltonian is a half kx squared. So this is the energy in a spring. You don't need this because I've told you that the wave function for a harmonic oscillator is of the form e to the minus kx squared. So what I'm asking you to do is to evaluate the perturbed Hamiltonian to first order, which will be equal to some normalizing constant. I'm just going to say a squared because it's going to appear twice here. Actually, let's not even do that. Let's not get complicated. Let's just put here phi of x unperturbed star h, oh, rather, I'm sorry, the perturbing potential, which I have said is lambda, just whoops, lambda x phi 0 of x, not star, dx. So I want to tell you to tell me what happens to that integral. And you can do it qualitatively if you want. You can do it quantitatively. I give more points if you do it quantitatively. Question 3. Explain qualitatively what including electron-electron interaction should do to the energy of bonding and anti-bonding states in the H2 molecule. So that is a molecule in which you have 2 protons, and the electrons and the bonding state, of course, are shared between these. So in the bonding state, the density of the electrons looks something like this. And in the anti-bonding state, it looks something like this. And now what I'm asking you to think about is the fact that because there are two electrons in this orbital, one spin up, the other spin down, they will have some repulsive energy between them. It'll increase the energy of the electrons. What happens to this state versus this state? So I will let you think about that. And then finally, the last question is just about the Hohenberg-Kohn theorem, which is a theorem that allows density functional methods to work. You'll see from the very last part of the book that these are very powerful. And actually, even for the chemists in the class who haven't taken any quantum mechanics, the chances are that if you have advanced enough versions of ChemDraw or some similar desktop programs for computing chemical structures, they're actually based on density functional theory. All right, let us clear my whiteboard because we're going to change topics altogether now. We're going on to chapter 3. Chapter 3 is about statistical mechanics and also goes on to chemical kinetics. So these are the sort of tools you need to understand fluctuations in nanosystems, which, as you will have seen from my introduction, I regard as at least as important as quantum effects in small systems. So let's now, and by the way, you'll see this coming into the theory of chemical reactions in chapter 8, I believe. Okay, so the question 5 is about the Boltzmann distribution. So this says that the probability of finding a system at some energy E is proportional to, and the constant of proportionality comes up by integrating the probability over all energies so that you can set that equal to 1. That will give you a normalization constant at E to the minus E over KT. This is the famous Boltzmann result. And I want a T in there. Okay, so apply that to the potential described in the problem, and you should find this trivial. Question 6. Calculate the statistical weight for all possible states, heads, tails of 4 tossed pennies. Statistical weight, very important concept. The statistical weight of a system, given usually by a symbol omega, is the number of ways a given macro state can be achieved by micro states. In other words, the more microstates that give rise to the same macro state, the greater the statistical weight. And then, as you will learn in this chapter, the entropy is given by k logarithm of omega, where k is Boltzmann's constant. So let me give you a really trivial example. It's 4 coins. If I want 4 heads, I'll have to have head on toss 1, head on toss 2, head on toss 3, head on toss 4, and any other outcome isn't going to work. There's one and only one way of getting that. So for this particular configuration, the statistical weight would be just 1. I want you to work out the statistical weight for all possible configurations. All right. The next question is about the configurational entropy of a one-dimensional polymer. In the text, I give an example of a one-dimensional freely jointed chain. So this is a really trivial example of a polymer. This is where a link can go forward like this, and then the next link could go backwards, or it could go forwards, and so on. And the walk is random. And then I give you a result in the book for the configurational entropy of this chain, given some length. So that, for example, if we want the chain to be fully extended, let's just say we wanted this to be the outcome. There's only one way of achieving this. So omega is 1, and so the configurational entropy will be k log of 1. I ask you to do it for a number of lengths, and so that you should be able to do quite easily. There is a formula given in the book for this walk. I'd like you to understand where it came from, but it's now an example of configurational entropy that's a bit more sophisticated than tossing coins. Finally, we're getting onto some physical chemistry. I ask you to work out an expression for the Debye length of a divalent salt at a particular, as a function of concentration. I give you a result in the book for the Debye length of a monovalent salt. So, for example, sodium chloride, the Debye length for a monovalent salt, I'll put one here. I give you 0.3 times the concentration. Oh, hang on, let me get my eraser again. 0.3 nanometers over the square root of the concentration of the salt in moles. And I ask you now to look at the Debye formula and work out what it would be for a divalent salt. The Debye formula is very important, and you'll read it in the book, but where it comes from is the balance between entropy, the fact that the ions would like to be equally dissolved throughout the solution, and enthalpy, or energy, or the purely energetic part of the thermodynamic energy, which is the electrostatic attraction that would like to keep at a negatively charged electrode all the positive ions close by. And the balance between these two is set by the fight between entropy and the fight between enthalpy. And we actually solve that problem using a very simple linearized model of the so-called Poisson-Boltzmann equation. Poisson, because the Poisson equation tells us what happens to electric fields in the presence of a particular charge distribution. Boltzmann, because that expresses how the ions would like to be distributed as a function of energy. So that's it. Let me wish you well with the homework and hope I can control this window and that it has really recorded.